Okay, welcome to today's lecture, which is going to start with a very important topic in fluid mechanics, which is on kinematics. So, in this particular part, we are going to look at motion in a fluid. So, the first part we are going to look at is description of fluid motion. So, that is something which we will get started off. How does it differ from what you have traditionally done in the case of particle mechanics? How does it disagree or differ from that? Then we will go to flow visualization. So, we will look at if you had to actually investigate a flow and understand what is going on, primarily from an experimental point of view, and also if you were trying to process data and do it in a numerical simulation. Flow visualization plays a big role, and it also gives us a way of understanding what is going on in the flow. And then the final part of this is going to be on deformation. So, we are dealing with a continuous medium which has a capacity to deform, and how do we quantify that deformation? How do we understand that deformation? How that deformation can be split into different kinds of deformation. So, that is where we will be. And while doing all of this, because the name is kinematics, we are not going to discuss about what brings about this motion, which is what dynamics is going to be about. So, there is something that initiates the motion, and we are right now trying to understand the motion and the description of this motion. What languages do we use to understand motion? So, if we get going with what you know, that is regarding particle mechanics was what you would have already studied, that if there was a particle under the action of some force and you know that its trajectory. So, you have the particle occupying some initial position, and then you have a trajectory for that particular particle that is given. So, xp of t, this is a trajectory of a particle. Again, we are not discussing how this trajectory is set up, but we have a trajectory, we have tracked this particular object. So, as we have tracked this particular object, we know that given this particular trajectory, which is the particle position. So, I have used a label p, which will get evident soon, xp. This is the particle position at a given instant of time t. And if I were to take derivatives of this, which is I take a derivative with respect to time, that gives me my velocity. If I were to take a derivative once more, I get acceleration. So, fairly standard things which we all know when we are learning about kinematics, that if I were to actually find out what the particle's position is at different instants of time, I can actually compute what is the rate of change of that position, which gives me my velocity, and then what is the rate of change of that velocity gives me my acceleration. So, no surprises here in terms of what we understand in particle mechanics. So, if I were to view a fluid in terms of particles, so I am basically now saying that let us think of fluid being made up of particles, and by particles here I do not mean molecules, I do not mean fluid molecules, rather I am saying that there are these infinitesimal elements in the domain where I am basically going to track these fluid particles. So, it is a thought experiment where I am now thinking that if I were to track, so let us mark a region. So, I am going to basically mark out a particular region which has these points are located, and let us choose a point here which has a coordinate. So, I will choose a point O which has a coordinate A. So, again you can think A is the position A1 which has components A1, A2, A3. Now, at a later time instant, if I where to find out. So, I have basically marked some points. So, these are basically points that are grid kind that I have marked out, and now I ask the question, where is that point A going to be located? So, what was at some initial instant a point O which is at A, that point is going to now move and probably be somewhere here, which is now labeled as a point xp. And then you could ask that all these points inside this red circle, where would it be? Now, each of those points inside that red circle could occupy a form like this. So, what I have done is every point inside that circle, I have basically mapped it by the flow and it lands up in this new region. So, the flow is a map which takes every point which was in this initial region, if I mark it as S0, to this region which I am now saying is some ST. So, if now you were thinking in terms of a particle's position, any particle's position is not just a function of time, but it is a function of its initial coordinate. Given that it started out from the point A, you can actually find out where it is going to be located at a given instant in time. So, A is the initial coordinate. So, now this tells us that if I am trying to give a description based on how I do it in a particle point of view, every fluid particle gets mapped by the flow and it lands at some location where the location that it lands on depends on where it was initially. So, if I say at t equals 0, it was at A. So, xp at t equals 0 is basically my coordinate A. So, it is this kind of a mapping from one point in space to another point in space, and this will apply to the entire fluid. So, this description, which is what we have done, we haven't given a formal name before, but we have always been doing this earlier, is a description that is known as the Lagrangian description. And you will see we are introducing a terminology here because we are going to introduce a different way of looking at things. So, the Lagrangian description, what it does, it says that I am basically tracking fluid particle as it moves in space and find its location given its initial condition, that was A. Which means if you mark that initial region, let us say S0, so now I am not drawing the particles inside, I have just drawn a boundary. This boundary gets mapped by the flow. So, at a later instant in time, this region could look completely different. So, this is at t equals 0 and this is now at the current instant of time. So, the Lagrangian description is basically tracking fluid particles as they move in the flow, and you are basically trying to say that each of those points, their trajectories are known given their initial location. So, if you say that I was located at a point A1, A2, A3 at a given point in time later, my coordinates are going to be xp1, xp2, xp3. These are my positions if I were starting out from the point A1, A2, A3 at a given instant in time. Now, this is all that we have been doing previously without a formal name being given, which is the particle point of view. Now, if we are thinking of velocity, the velocity, I will now put a label L here. The velocity from this Lagrangian point of view is because the position of a particle depends on two variables, the initial location and the instant of time. So, I will use a partial derivative here. So, this is going to be dou xp dou t at a fixed value of A. So, if I fix the initial position and I were to actually track the rate of change of my position, that gives me a velocity, which is exactly what I said earlier. I am now introducing the idea of an initial position. Now, this, if instead I go back to that same picture of a trajectory. So, it starts off from an initial point A and it is now located at a particular point A comma t. Now, at this particular point, at this instant, you have a particle that started off at A at t equals 0, which lands here. Now, I could also make measurements of velocity at this fixed location in space. Rather than making measurements moving along the trajectory, So imagine you have placed a sensor which could measure the velocity sitting on the fluid particle. So it rides the fluid particle, and at every point it gives you a signal of what the velocity actually is. But you could also make a measurement where you are fixed at a particular location and you are trying to find out what would be the velocity, which means at a given point in space, which is x equals x1, x2, x3, at a given instant in time, I can ask what is the velocity. So this is now borrowing on the idea that we introduced few classes back, which is the fluid can be treated as a continuum. Because the fluid can be treated as a continuum, I can actually define what is the velocity at different points in space, arbitrarily chosen at different instants in time. So if you want to take a slight coarse kind of an example of what this is happening, if you have this actually, instead of being a particle, imagine this was actually a car that was moving. So the speedometer that is there in the car, that actually throws back the reading of how fast the car is moving. Now if there was a measurement that was being made by a traffic cop at a particular location of the velocity of the car that is passing through. So you have you have speed guns or you have speed meters fixed at a particular location. As the car passes through, the speed as displayed at that instant on the dashboard of the car should be exactly the speed that is actually displayed by the instrument that is fixed on the ground. Unless there is some calibration error or some kind of a faulty equipment, they should be the same, which means the Lagrangian velocity, given that a particle started off at a particular initial location, should be equal to the velocity. So here, let me write this. So the Lagrangian velocity, given that you have the particle moving with a initial in location A, this is going to be equal to the velocity that you measure at a fixed location, which is x equals xp a comma t at a given instant of time. So the Lagrangian velocity only says that if you were to start off from an initial location at a given instant of time, you would be occupying these various positions, and the velocity which you are measuring at a fixed location, that is, now we introduce a field idea, that is the Eulerian description. So the Eulerian description gives us a field approach to make measurements, while the Lagrangian description gives you a particle or material approach to make measurements. So you have these different ways of actually making measurements of what would be your velocities that you can measure at a particular point. So we have the relation that the rate of change of your coordinate, given that it at a fixed value of initial condition, this is basically defined as my Lagrangian velocity, and this would be equal to my Eulerian velocity if I were to make measurements exactly at that same point where the fluid particle was passing by at that exact same instant. They should be the same, I mean they cannot disagree, but there are different ways of measuring. One measurement is basically you are following a trajectory, and as it passes through a particular point in space, at that instant in time, what you would measure as the velocity at that point in space should coincide with what you would be measuring if you are following the fluid trajectory that passes through that particular point at that instant in space. So there are two things to match here. You are measuring it exactly at that same point where the fluid particle is passing through exactly at that instant in time. So, these are the two approaches of looking at things. You could have a point of calculation, a point of measurement, tracking or tracing a fluid particle, which is the Lagrangian approach. You could also have a point of measurement, which is an approach that is at a fixed point in space. Now, it seems so far that if I were to use the Lagrangian approach, I just need to actually go about finding these. So, if I want to find what is the acceleration, I need to compute this particular quantity. So, this would be my Lagrangian acceleration. I am using A unfortunately for the same thing, but this is the acceleration, this is the initial label, the initial location. Now, it is quite elegant to use the Lagrangian approach, because you are actually treating things the way you think of how you treat a particle. If you think of measuring along a fluid particle, you just find out the rate of change with time, and that gives you what your velocities and accelerations are. So, when you think in terms of Newton's laws of motion basically tells us that F is equal to mass times acceleration, and so the acceleration would be force per unit mass. And now we have already seen that the acceleration from the Lagrangian point of view is the particle position, the double derivative of that, and this is to be equated with whatever is the force per unit mass. So, we should have stopped here and said that we have a way where we can do all of this just the way we have done it for particle motion. Now, as you will see when we start giving description of how to find out forces in a continuous medium, that the disadvantage of using the Lagrangian picture is actually finding out the internal response in Lagrangian coordinates. That if you are trying to actually find out how a fluid deforms, the deformation of the fluid following a fluid trajectory is a cumbersome calculation, and which is why when we do fluid mechanics, we mostly adopt the field point of view. The field point of view is where we are basically making measurements or doing force balance at a particular point in space. So, that is the bit which we will focus on, the Eulerian description. The Lagrangian description is not rare. You do use the Lagrangian description in several places when you are trying to, you don't have a capacity for making a point-wise measurement. You don't really have, it's not very easy to stick an equipment at a particular point and make measurements of velocity there. So, one classic example where this would happen is any measurements that are made in the atmosphere or oceans. For instance, if you want to find out the wind velocity, one thing that you could do is you can have a long tower fixed to the ground and you fit various sensors on that tower and that measures the wind speed. But it is limited because it is based on where all you can place these towers and you can only make it a certain height. It is not really that easy to make very tall towers, and in some cases you are interested in wind speeds several kilometers from the ground. You are not really interested in very near ground phenomena, you want to find out what is going on tens of kilometers away from the ground. So, in which case it is not practical to build towers that jut so high into space. So, what you would typically do is you would release, you do different things, and one of them could be you release, let us say, weather balloons. So, as you release these balloons get drifted by the wind and you are making measurement as it gets drifted. So, not just wind measurements, you can make measurements of other quantities. So, the Lagrangian approach is not just a measurement of position, velocity, acceleration. It can be any quantity. So, in this case, this thing could make measurements of temperature. It is finding out what is the temperature as it gets drifted by the surrounding currents. So, you are making measurement in those cases which is Lagrangian in nature. In the same way, when you are finding it in the ocean, and it's not that easy to like stick a pole all the way to the bottom of the ocean floor, especially in the deep ocean, where you get measurements of velocities and other quantities all through at a fixed location in space. That's not a very easy thing to do. If you want to typically do it, you would have a float that is actually moving on. So you track these floats as they drift, and as they drift, they're basically giving you data of what the currents are. What you can calculate what would be the currents on the surface of the ocean. You can make measurements of, let's say, temperature. You can make various kinds of measurements, but all the measurements are being made as this drifter is actually moving. As the name suggests, it is moving on in the open ocean. So that's a Lagrangian description. So Lagrangian description for measurements of things is quite common when you think in the geophysical context. But when we are going to do the force momentum balance and a lot of experimental setup that is done at a smaller scale, the Eulerian description is what is prevalent. If you have a flow through a pipe and you want to find out the pressure, you put a static pressure tap, or you want to find the velocity, you have a current meter at that particular location. So these are all at a fixed location. So now the question is, how is the acceleration? Because we saw that this is the Eulerian velocity. How do I find the acceleration and relate it? Because here, when I am writing my Newton's law, I am relating the rate of change of my velocity, which is the acceleration, to the sum of all the forces that is acting on that fluid parcel. So how do I do that? So as you can see that the Eulerian description is a function of the position and the instant in time being independent variables. In the Lagrangian description, the independent variables were your initial condition and the instant in time, whereas here the independent variables are your position in space and the instant in time. So if you want to now say that I have an increment of this particular quantity, then you will have dou u e dou t dt plus dou u e dou x dx. Now if I am interested in calculating what is the rate, what is the acceleration, because these two should agree. So now if I want to find the acceleration, what I am interested in, I want to find out this quantity at a fixed location. What is the rate of change of the velocity, the Eulerian velocity that I am measuring? So I am defining a time derivative for when it starts from an initial position A. So this would be dou u e dou t plus dou u e dou x dotted with dou x p dou t at a fixed value of A. So this gives us a very important relation, which is that the acceleration that I am interested in, so let me write it. So the acceleration that I am interested in, given that it starts from the same initial location, is dou u e dou t plus u e dot del u e. So the object that we will have appearing, sometime you write it with a capital D, ddt. This is what is known as the material derivative. So I am dropping the E from here, because here onwards we will refer to everything as the velocity field. So I am not going to continuously keep carrying E, but this gives us a crucial information that how is acceleration to be measured at a given point in space. And you see there are two key parts. So if you focus on these two pieces individually, the first one is the rate of change with time. So this is an unsteady component. So if you again draw a grid in space, and let's mark a particular point in space. So, at this particular point in space, if you were to make measurements of, let's say, velocity, and the velocity at that fixed location, I'll call this location as, let's say, point P. So, at that particular point P, if I make measurements of velocity, if the velocity was continuously changing with time, then I would have a non-zero contribution from this term. So, that's an unsteady component of the acceleration. But the second term, which is u dot del u, this term is known as the advective, or some cases the convective component of acceleration. And the part that's important about this term is that at that same location P, if the velocity was not a function of time, the velocity was constant in time, but the velocity at point P and its neighbor O Q. So, in these neighboring points, if the velocity is measured in point O, point P and point Q, they are different. So, your neighbors are moving, or neighbors give you different velocities, then I have a velocity gradient in the problem. So, u dot del u is going to give you a non-zero term even if your velocity is not explicitly a function of time, because you have spatial variations of velocity. So, the fact that your acceleration has these two components is an important thing to understand. So, when I say there is a steady flow, if I use the term steady flow, what it means that the velocity at a given point is only a function of the spatial coordinate. It is not a function of time. That's what it means by a steady flow. So, if you have a steady flow, the acceleration at a given point is not guaranteed to be 0. Because in a steady flow, if you have the velocity to be a function of space. So, I will take an example. So, let us say I will take a one-dimensional velocity field. So, u is along the one direction, just a single 1D velocity field. So, let us write that term out, dou u dou t u dot del u. There is only one component of this object. So, this becomes du1 dt u1 dou u1 dou x. The first term is 0. The second term is x dou x of x, which means this is non-zero. So, the acceleration a1, if a1 is the acceleration, is x, is non-zero. So, you have acceleration in a fluid due to spatial variations of velocity field. So, we will see this a little bit now further when we talk about flow visualization. So, we got introduced to the idea of an Eulerian and Lagrangian description of understanding things, and now we will see that this Eulerian and Lagrangian description, how it also gets connected when we are talking about flow visualizations. So, starting off with the idea of a velocity field. So, I have the velocity given at all points in space at all instants in time, which means at a fixed instant in time, if I draw my grid I know what is the value of velocity at all the grid points that I have. So, at all these points I know what is the velocity. And let me try just drawing the velocity vector at every point. So, I can find what is, so I am drawing it in 2D. You can think of this in a 3-dimensional example, that at every point I can actually find out what is the velocity component at that particular point, the u1 and u2. So, I have these arrows, the direction of the arrow gives me the direction of the velocity field, and the length of the arrows tell me the magnitude of the velocity field. So, now I can think of curves where the tangent at every point gives the velocity vector. So, I want to visualize this, and so I say at this particular instant in time, this is the description of the velocity field at every point. I have just drawn some few points, but you can draw this at any arbitrary point. And now I am saying that I am interested in curves where the tangent at any point gives me the velocity vector at that particular point. Now, how do I express this mathematically? So, if I have a curve, so I'll draw something which seemingly is a curve where it satisfies this property. So, if I take a small segment of that curve, so I will call this dx. Dx has dx1, dx2, dx3 as its component. It's a small line element. So, if it's a tangent, then the property is dx cross u is equal to 0. That's the idea of it being tangent, that if the velocity vector at that particular point is tangential, then u should be parallel to that line vector, that differential line vector that we have, which if you now write it out, this cross product for it to be 0 would give you dx1 by u1 is equal to dx2 by u2 dx3 by u3. This comes from dx cross u is equal to 0. You can write this cross product individual component form, and when you write it individual component form, you will get. So, if you write the component 3, the component 3 would be dx1 u2 minus dx2 u1. This is the component in the third direction. So, it being 0 gives you this term, and similarly you can work out the other terms. Now, this is what we first get introduced to for visualization as the equation for streamlines. It's a very important idea when we are looking at flow kinematics. It gives us description where you have curves in space, where at any point on those curves you have the tangent gives us the velocity vector, right? And the most important thing to remember when you are finding these streamlines, that this is at a fixed instant of time, which means if I write this out explicitly, let us say u1 is going to be a function of u1 of x1, x2, x3, generally that is what it is a function of, and there is t. And let us look at the second equation, which is dx2, u2 is going to be a function of generally, which means you need to integrate this and write it as dx1 dx2 is equal to u1 x1 x2 x3 comma t divided by u2 x1 x2 x3 comma t. When you do this integration, consider t to be a parameter or t to be fixed, which means when you are finding the streamlines are found for a fixed value of t. Whether the velocity field is a function of time explicitly or it is a steady velocity field, irrespective of that, when you are calculating streamlines, you need to consider t to be a fixed parameter and do the integration. So let's take examples and let's solve this and see. So let's take a velocity field where u1 is x1 and u2 is minus x2. Very simple two-dimensional velocity field. So x1, x2, x3 are the three Cartesian coordinate, u1, u2, u3 are the three corresponding Cartesian components of velocity. So you have a two-dimensional velocity field here. So let's just start with dx1 by u1 is equal to dx2 by u2, which gives us dx1 by x1 is equal to dx2 by minus x2. So if I integrate this, I get ln x1 is equal to minus ln x2 plus some constant, which gives me x1 ln of x1 times x2 is equal to a constant, gives me an equation that is x1 x2 is equal to a constant, right. So if you now try plotting it, so this is x1, this is x2. So what we got, the equation for the streamlines is x1 times x2 is equal to constant. So these are nothing but family of rectangular hyperbolas. So how do you plot these streamlines? You choose a particular value of constant. So let's say you choose the constant to be 1, in which case you have to draw a curve which is x2 is equal to 1 by x1. If the constant was, let's say, 4, in which case you draw the curve which is x2 is equal to 4 by x1. So these are families of streamlines that you are going to obtain. The constant could also be 0, x1, x2 is equal to 0, in which case your streamline could either be x1 equal to 0 or x2 equal to 0, which is effectively your y-axis and x-axis. So the axis, these two are also your streamlines. Now this is a problem which was steady. There was no time dependence in the problem. So there was nothing particularly for us to be very careful about. Let's revisit this problem and consider the velocity field where u1 is x1 times 1 plus t, x1 divided by 1 plus t, and u2 is minus x2. Okay. So now if I let's make it a little simpler. I think we'll make it more complex as we go on. So let it be x1 times t. It will become more difficult as we go on. So u1 is x1 times t, u2 is minus x2. Let's do the integration once more. So dx1 by u1 is equal to dx2 by u2, which is dx1 by x1 times t is equal to dx2 by minus x2. Now this is where you have to pay attention. When you are next going to find the streamline, consider t to be a parameter, fix t. In this integration, t just plays the role of a parameter, nothing else. So when you do the integration, you have 1 over t ln x1 minus ln x2 plus some arbitrary constant. Okay. So if you do this, you will have ln of x1 raised to the power 1 by t, x2 is equal to some constant, right. I could also write it as ln, or rather also I could write it as x1 x2 to the power t is equal to some constant, because t here is fixed at that particular instant. So this now gives me the equation of my streamlines, and as you can see, that x1, x2 to the power t is equal to constant. For t equals 1, I get rectangular hyperbolas. But if I go for t equals 2, now my equation is x1, x2 square is equal to a constant. So, this is a steeper curve than x1 equals to 1 by x or x1 equals to constant by x1 equals to constant by x2. It is now steeper than that. So, as it progresses with time, the streamline pattern at different instants in time would look different. And this tells us that streamlines for an unsteady flow. So, you all understood what I mean by unsteady. Unsteady means that the velocity is an explicit function of time. It is explicitly depending on time. So, for an unsteady flow can change with time. Now, why did I say can change with time? Why did I not say that it will change with time, that for every different instance of time it will be different? So, if you consider a velocity field which is u1, I will keep taking the same example, u1 x1, some arbitrary function of time, and u2 is minus x2 with the same function of time. Now, you do the exercise dx1 by u1, dx2 by u2, and this gives us dx1 by x1 function of time, dx2 by minus x2 function of time. Now, we have already said that t is a parameter. T is to be considered fixed when we are finding the streamline, which means I will get back the same equation for a streamline, right? So, this is to say, now if you can ask the question, why is this the case? Why is the streamline pattern not changing even though the velocity field has some time dependence? Why? What would be the reason? So, one way to see the reason is that if you plot the velocity field at any point, choose some arbitrary points and draw the velocity field. Let us say it looks something like this. The velocity field at a later instant of time will have the same direction but different magnitude. Because you can see u1 by u2, the ratio of u1 by u2 gives you the angle made by the velocity vector with the horizontal axis. So, the angle does not change, which means the velocity field, if you take a picture of the velocity field, the direction of the velocity vectors remain unchanged in time. What is changing is the magnitude of the total velocity field with time. You can multiply this with some sin t on both sides, which means at a given point in time, the velocity, or given point in space, the velocity is oscillating. But if you plot the velocity vectors, it is by the same amount everywhere the velocity is actually oscillating. So, direction of the velocity vector does not change. So, this is a very special case, which is why I use the word can here. This is a very special kind of an unsteady flow where both the velocity vectors are multiplied by the same functional form in time. So, this is what will take us to what would be our next topic, which is we have now said that I have a field description. So, in the field description, I know the velocity at every point in space. I know the velocity at every point in space, and thus I can actually construct these curves which are streamlines such that at any point in space I can basically have the tangent to these curves giving me the velocity field. Now, going back to our original idea that we started off with, which is saying that I have a particular point which was initially located at some location position. Let us stop using A. I think we are landing in trouble with A quite a lot. So, I will use a different notation xi. So, if it was initially at this particular point, then it lands here. This was our Lagrangian description. So, what we will do next is, can we visualize the flow using a Lagrangian description, which means if I were to release a small blob of dye or a small tracer particle, you will hear this word quite often, a tracer particle, just to say that you are introducing something into the fluid whose motion tracks how the flow moves, but it is so small, it is so tiny that it does not really come back and alter the flow. So, you introduce a tracer particle, and with this tracer particle you are trying to track its motion. So, how is it going to actually move? So, this is what we will pick up next, and that would be the idea of path lines. So, we will take this up in the next lecture.